Okay, welcome everyone to this last day of the workshop. And it is a great pleasure and honor to introduce Claire Tomlin. Claire did her undergrad in Waterloo and Imperial, then went for a PhD in Berkeley, did quite a stint in Stanford before coming back to Berkeley. I don't think I really need to introduce you, but she's done amazing work in hybrid systems, both on the control side and on the more CS side, I would say. A lot of work on multi-agent decision making. And I think she has a career where she really connected very fundamental results with actually flying drones. And so it's always a great pleasure to see her talk. So with that, Claire.
Thank you, Sebastian. Thanks for this workshop, which is very timely. It's kind of a time when things are changing very quickly. And I think for people working in control and automation, the big change is, of course, the advent of foundation models and the potential use of those in automating systems. And my area of research which is in safety critical control, is one in which there's, potential great gains of using foundation models. So models that are really stemming from large language models in automation. But the challenge is, of course, for safety. And we're used to making guarantees to within the limits of the assumptions of the models we're using. And the questions are now, how do we try to think about using some of these really state-of-the-art techniques in safety critical control? We're not there yet. I think it remains one of the big challenges, even as we get more and more high performance systems using large language models. We've only started to work on this in my group, but we've been working on integrating AI into safety critical control for a long time. So I'm going to tell you a little bit about what we've done in the past, and then I'll end by talking about some of these new efforts, including work with Sanjit and others, thinking about how we bring in this idea of like the symbolic nature of the large language model or the foundation model into getting a better mechanistic understanding of how that system is behaving, especially with respect to safety critical control. So maybe I should have called this Towards AI for Safety Critical Control, but we're not there yet. Okay, yeah, as Sebastian said, we've been doing a lot of work with drones, with aircraft, with air traffic control, and other systems as well, marine systems, seaweed growing platforms, for example. And I enjoy that. I like working at the interface of really interesting application problems and the theory and algorithm development in control and AI. We've, these are applications, or these are systems, many of which exist today or are up and coming, like Joby Aviation is a Bay Area company that's designing an air taxi, which has the potential to be used for short haul transport across large urban areas. So you can get from here to the South Bay in less than half an hour, which you can't do if you drive. And the models that they're using are really interesting. They're a vertical takeoff, and then they switch. There's a transition mode in the air where the rotors actually, or the wings and the rotors are tilt rotors. So it transitions to a conventional mode. And that, of course, is a very safety critical maneuver. Those types of aircraft have existed for a while, but they're usually flown in the military, and they fly them very conservatively. Air taxis would like to automate a lot of this. So how do we even think about automating safety critical maneuvers like that? On the far left is a snapshot from work we did with air traffic controllers. And here, this is, of course, another safety critical system. If you're thinking about automating some of the functionality of what air traffic controllers now do manually, and the complexity here, and the reason it's such an interesting control problem when you're automating it, is because of the multi-agent aspect. So this is a system where the complexities, you can imagine quite simple models of an aircraft flying through space at that level, but the decision making and the coordination and the like air traffic control ground versus decision making in the air, all of that is really to be determined in the future. And when we think about automating in multi-agent scenarios, how do we take into account all of the possibilities, and how do we prove things about the result? And really, what does a proof mean when we get to the point of looking at AI introduced into these systems? So those have been motivations of me and my group for a long time. First, safety. I put simplicity as number 2 because these systems will remain in some part a system where the authority is shared between the human and the automation on board. And so when you're designing automation and you have the ability of a human to come in and take over or to share that control authority, there has to be an understanding, there has to be a representation of that automation of that system, which works well with the way the human controls the system. So even thinking about that is an interesting and challenging problem for formal methods. And then, of course, in any automated system, and the reason that we're so excited about using automation, but AI in particular, is that ability to adapt to new information. Okay, so I guess my whole career, I've been working on safety filters, and I put that, as for even in like very old control systems, you're where this may be an automated system, maybe your planning is also automated, so that's been around for decades. The safety filter represents a kind of a system which is getting information from the environment about constraints, about new systems that are arising in the vicinity of the aircraft. It's also getting information about, the system that you're trying to control itself. And that safety filter is responsible for basically providing guardrails on the behavior of the system and adapting to constraints that arise. So, so even if your automation is unaware or provides a directive to follow a particular control, if that control is going to cause the system to violate a constraint, the safety filter should be able to filter that back and keep the system safe. And so that has been a kind of guiding principle of our group for a long time. And from the beginning, even before we started integrating AI into the systems, we've been developing model-centric, model-based techniques for computing safety filters. We have been looking at continuous dynamic systems like this one represented here. We've been looking at finite state machine models of systems. We've been looking at hybrid systems, which combine those finite state machines with continuous models. And all of these systems, all of these models representing these systems can have some uncertainty associated to them. We usually model that as a disturbance where the actual action of the disturbance is unknown, but there are bounds on it. So we represent either, deterministic bounds or a probabilistic representation of that uncertainty, and then design the safety filter, which is the control, so that the system maintains its specifications. It maintains that safety specification despite the disturbance, despite the possible worst case action of the disturbance, or in a probabilistic sense, the behavior of the disturbance. A lot of our work has been using game theory to represent that control, to design that control. We think about control and disturbance as two players in a multiplayer game where we're pitting the players against each other, and we're designing the control that will keep the system safe despite the worst case uncertainty. And our focus has been in computing safety filters. We use reachability, so a kind of model checking representation of this problem, where we compute those sets of states for which the system remains safe, for which you can find a control such that the system remains safe for the worst possible uncertainty. And our this is a visualization of the problem for in three, well, in two dimensions, but three as we think about the representation of that reachable set, because we have been working kind of with the heart of our method is a level set representation of these sets. So we define functions whose zero level set represents the set itself. So if this is a target that you'd like to get to, here is the solution of our reachability problem, which is posed as a Hamilton-Jacobi-Isaacs differential game or partial differential equation representing that differential game. And so one at any time can capture the zero level set of that function, which represents at that snapshot in time the set of states for which the system can reach that target set despite the worst case uncertainty. And then things like adding constraints, like a set here, which you'd like to avoid. Again, a representation of that set as the zero level set of some function. You can adapt the problem and then compute this so-called reach avoid operator, how to reach a set of desired states while avoiding violation of constraints. Okay, so then, and you're always capturing that zero level set. Thanks to former PhD student Sylvia Herbert for doing the nice animation for that. She's now at UCSD. Okay, so immediate questions come to rise. The computation of that is a challenge. This is, two-dimensional state. This visualization is two-dimensional state space, three-dimensional problem overall. And a lot of the research that we've been doing up to and including the time we started about a decade ago when we started integrating AI into these methods has been in developing computationally efficient methods for solving this problem in high dimensions. Now, what does high dimension mean? Well, using some of the tools that I'll briefly mention, we're up to about like 20 to 30 dimensional continuous state dimensional problems, which I think is, it's great. It's good when you're considering, a particular control system or maybe a small group of vehicles where you have to have a representation of each of those states and their interactions. It doesn't scale to the huge numbers of states that we see in in a deep neural network, for example. So we and a lot of other groups have been thinking about methods to scale, much more broadly. And I'll mention a few of those. This is early work we did when I was still at Stanford, when we kind of posed as maybe a kind of litmus test of this. We posed multiplayer games. This is actually inspired by a real pursuit evasion game that Rufus Isaacs used in his work developing the Isaacs game. And one can show that set of, in this case, unsafe states, so where the pursuer could be and the aircraft wouldn't necessarily stay separated by that requisite distance. As you change the assumptions on communication, ability to measure state, for example, that set can become quite conservative. So for example, if you have very little information about the behavior of the other aircraft, then you have to assume your disturbance set becomes bigger, and the set of states where you can't be, if you want to guarantee that there's no collision, becomes much bigger. Right, and here's as I said, it was kind of a litmus test. So this was back when you couldn't buy a quadrotor very easily. We built these. This is the early 2000s. There are 4 quadrotors flying around, 4 students joysticking them around. Each quadrotor is running that collision avoidance algorithm with respect to each of the other 3 quadrotors. So around each quadrotor, you see 3 sets, which represent the reachable set. This is the unsafe zone for each of those 3 other quadrotors. And this is just a snapshot. You can see the experiment going there. So the students you can see them over there. They're joysticking the quadrotors around. They're trying to get them into regions where they're close to each other. And then when one vehicle touches the boundary of its reachable set with another, the automation takes over, applies that optimal control, and separates the aircraft. And then it keeps it away from its reachable set. And then at some point, the control authority is given back to the student, and then they can joystick the aircraft around again. There's a couple of things to mention about this. First, this is not a real multi-agent problem. This problem we were able to solve pairwise. So this problem you can prove that the safe solution is actually the union of the safe solutions for each pair. That decomposition doesn't always hold. It holds here because of the dynamics of the system. One of the safe actions is the vehicle can actually hover in place. And we're solving these, we're assuming these vehicles are all flying at the same altitude. So that's an interesting question going forward.
So you mentioned that once it's safe, then control can be switched back to the person who's. So how was that determined? What was the condition?
Yeah, that's a really good question. We determined in this experiment, it was just a certain distance away. This is not how you would design a safety critical system where the control authority is being shared, like I talked about before. But it was an experiment to try out this technology in a multi-agent scenario. And that question is actually, when you're switching between human control and automation, how do you do that? Not only the kind of human-computer, human-machine interaction, but also what information, theoretically, what information does the human need to know to be able to take over safely? So that was not part of this experiment, but we did incorporate it in a kind of, very kind of brute force way, I would say. And then since then, we've been doing a number of experiments which involve collision avoidance with interesting obstacles, including people. And these are experiments that we did with former students. There's Sylvia again, Jaime, Ellis, looking at using predictive models of human behavior. In this case, it's pedestrian behavior, predicting probabilistically where the people are going to be over the course of time, and then developing a reachable set, but also a control plan that avoids not only where the person is, but where we're predicting them to be, and then updating that prediction based on how the human is behaving according to the model. This is a project, so we, with Sanjit, we are soon ending actually a very long-standing DARPA-funded project called Assured Autonomy, which was really, I think, it's been a wonderful project. It started around 2017, so it's been going on for us for quite a while. But the idea was to be able to integrate machine learning-based components into a control loop, just like I had been showing at the beginning, and then make assurances about the overall behavior of the system when you've got, for example, perception that's done with say a convolutional neural net or however it's going to be done now, but you have a control system around that. You have to make decisions based on the output of that machine learning component. So Boeing was our partner in this collaboration, and we asked the question, if you are, acting according to a machine learning based component like a perception model, what happens if you get errors? If, for example, your perception goes down, suddenly your eyes, your cameras go off, they're clouded, your eyes are closed. How can you use this kind of safety filter technology to say, okay, I know exactly where I was relative to that van when my sensor went down. Now I've lost my sensed information. I'm going to do worst case projection based on the dynamics of my perceived dynamics of that other vehicle and maintain safety. So I'm going to be very conservative, but I don't, in this case, the safest action was to stop. But in general, you're avoiding not only the vehicle, but the projected set of where that vehicle could be. Okay, so talking about scaling. So this, as I said, this computation of that PDE, we were doing it using basically numerical computation methods for solving PDEs. And we have a toolbox that we developed, actually a number of instantiations of this reachable set, level set toolbox it's called. But it works. The largest problem we were able to solve directly without doing decomposition methods, is a less than 10 continuous dimensions. And so, as I said, we've been working on scaling these methods. And with Samuel Bansal, we developed a learning-based method for solving that PDE. So here it's kind of integrating AI in a different way than I talked about earlier, but it's recognizing that numerical solutions to PDEs are a big, they're a big problem. People use them all over the place. And in high dimensions, those are essentially unsolvable. So how could we leverage the idea of using a neural net, which is very good at choosing relevant samples and doing computation at relevant samples to be able to approximate solutions? How do we use that functionality of that neural net being a good approximator to develop approximate solutions of that PDE? And so we did that. We developed a method which is basically trained. So you train the method that solves the PDE using the PDE itself as the loss function. And then, and with random or more judicious methods of sampling the states to be able to compute that loss function, you can solve that PDE in high dimensions. And those, so one of the recent problems that Samuel has solved with this is 26 continuous state dimensions. Now, you're computing an approximation of that PDE. It's in general hard, and it took a lot of time to come up with a method to do that, which approximates well what the numerical solution would give, which of course you can only test in low dimensions. But the heart of it was using a sinusoidal representation network that came out of a computer vision problem as the activation function. Because it's a PDE, you have to not only compute the activation functions, you have to compute their derivatives, and sinusoids are smooth. So there's a nice property in terms of computing the derivatives. And we call this deep reach, for deep learning of reachable sets. So one of the first problems we solved using deep reach was a 9-dimensional collision avoidance problem. So that's 3 aircraft, 3 dimensions each. And this was a problem that we weren't able to solve previously. So again, this is a multi-agent problem, but you can't decompose it into pairwise here because the vehicles can't hover, they're aircraft. And so here is just a projection of the solution in green, which would be if you computed pairwise and then you looked at the joint reachable set. So what we did do for the quadrotors. And in purple is the deep reach solution. So you can see there are states which are outside the pairwise and inside the deep reach solution, which if you look, for example, at an initialization of the pursuer with these 2 evaders there, you can actually lose separation. So you cause the vehicles to be such that there's a maneuver such that any pair of those could lose separation. But if you sample along the boundary, just outside the boundary of the pink set of the deep reach solution, so here's a sample, you can see that you're not actually losing separation. So it's not a proof, right? It's a good computation, we believe, that's approximating this reachable set. But how do we validate it? We validate it by sampling. And so the question is, how does one develop a more confidence in these learning-based solutions? And so over the past couple of years, some of the work that we've been doing is in taking those learned reachable sets and certifying them, developing methods to do a certification on the learn-based solution. This is right now we're doing again, I call it a kind of litmus test of this work. We have a drone racing. So these are smaller drones now. They're little crazy flies that we're flying in our lab in Quarry Hall. And we're asking the question, how do we learn these reachable sets? So again, 4 drones, high dimensional reach avoid sets. But then how do we post-certify those? And do we have a method that we can do ahead of time? Do we have a method that we can do in real time? And so this is an answer to that question. Here we were looking at higher dimensional models for each drone, where drones can fly, really in 3 dimensions. They can use their downwash to kind of go over their opponent and block it out of the way. So if you fly over another vehicle, it just flies off. So then reach avoid is trying to get to, fly through these loops as part of the course while avoiding the downwash of the other vehicles. And so we have computed, this was using a different method for learning the reach avoid set, one that was developed by Jingqi Li in my group. but different from deep reach, but in the same flavor. And then how do we then go ahead and certify those? And we've developed, so this is the learning-based method. We use two methods for certification. One is actually using the properties of the dynamics themselves, so the Lipschitz continuity of the dynamics and the value function, and the other is using an optimization-based method. Both of those have versions that can be done, have approximate versions that can be done in the real time that a drone racing problem is flying in. So here's let me just show you the video. That's a downwash. You're just trying to like show that if you fly over that vehicle, you can basically cause it to fail. So we're looking, in this case, we're still looking at pairwise reach avoid computation, but we've now blended this with an overall drone racing problem. I don't actually have a video of that now, where we're using iterative linear quadratic games combined with this online reach avoid, certified reach avoid calculation to do drone racing around the room. That's actually being done right now. There's a group of students that are working with Jingqi that are filing their masters on this, and they spent the year working on that implementation of those two techniques. Questions?
Can you say a little bit more about these Lipschitz constants? Where did they come from? Are these Lipschitz constants for the neural network, or are these inherent properties of
They're Lipschitz constants of the dynamics themselves and of the value function representation, so not of the neural network. So we develop, we use this neural network representation to learn this value function, where this value function has a Lipschitz guarantee associated to it. And we assume we know those. So we can come up with maybe kind of loose approximations of that. And the more you know about that Lipschitz constant, the tighter the approximation is. So that's something that it's just been published, it's just been accepted for publication. And you have to know something about the problem to be able to use that certification.
Okay, thanks.
Yeah, I just wanted to clarify the notion of certification here. So so it's deep reach, or the other method computes the reachable set or the approximation of the reachable set. And then once you have that, then you can use second order conic programming or the other method to verify that that is indeed an over approximation of the true reachable set. Is that how what is happening?
Okay. Yes,
right.
Exactly. I'd like to just I actually don't know what, oh, good clock. Okay, I'm going to spend just a few slides talking about some very recent work we've been doing. And this is relevant. I talked about that Joby aviation problem. So in some cases, you don't know your dynamics. And, in a lot of robotic systems, you design the system so you know the dynamics and you don't really need to learn it. I think that's one of the principles we should be thinking about. How do we bring a lot of known things like dynamic models into these problems? But that transition mode where you're going from a vertical flight mode and then you rotate your rotors and you've got a conventional flight mode. In that transition mode, the flight dynamics are not well characterized at all. There is no existing model. Even the people who design these aircraft they have finite element models that represent from testing that represent these dynamics. So one of the questions we had is, and in general, in robotics where you're dealing with soft tissue or you're manipulating something that isn't well characterized, there is a very interesting class of problems where the dynamics themselves are unknown. I think it's also an interesting problem when you're using foundational models for control. So now you've got a closed loop system where essentially the dynamics are unknown because you don't know what this foundational model is. It's too big to characterize. So one of the methods that we've been working on, and this is part of the PhD thesis of Jason Choi, who's also graduating this year from my group, is how do we develop data-driven construction of reachable sets? So what do I mean here? That you have, there is some underlying dynamic model, but you basically don't know it, or you don't know something about it. Actually, the only thing we're assuming that we know about this model is the Lipschitz, that it is Lipschitz continuous, and that you know that Lipschitz constant. If you don't know it, you approximate it. And again, we have this conservative, like you can scale that as better models, you get a better representation. Okay, so the essential idea here for this data-driven method is characterize, so the unknown dynamics in general, U as your control input ranges over a set. So this is like a differential inclusion. Let's just characterize that as, say, like a vector field bound, a velocity, an overall velocity. It's a multidimensional state vector. And when we're computing the reachable set, a key heart of that is computing the Hamiltonian. That's part of like how the dynamics interface with the overall behavior, the gradient of the value function itself. So if you don't know the dynamics, you don't know the Hamiltonian. And you don't actually, so the kind of thing is here, if you're all you care about is like this Hamiltonian and computing safety based on this Hamiltonian, you don't actually need to know the dynamics, you need to know the Hamiltonian. And that problem itself can be posed nicely, the problem of identifying the Hamiltonian. So that's the key idea here, representing the dynamics as a vector field bound, and then representing the Hamiltonian in terms of that vector field bound. This problem of computing the Hamiltonian is kind of close to a convex optimization problem if this were convex, but it's not. But maybe we can make it convex. And maybe by sampling judiciously, we can turn this problem into a convex optimization problem. And that's what Jason did. So that Hamiltonian, if we think about, okay, what are we doing in general when we're flying that, maybe Joby's taking flight tests and capturing both the control input as well as the resulting dynamics. You're capturing a trajectory, which includes input and state information. So those are your data points. How might you use those data points to come up with a convex approximation of that overall vector field bound using samples? And the way the computation of that the optimal Hamiltonian works becomes a max-min problem where using the samples, you're basically computing the worst case sample over all possible samples and using that as a way to characterize a bound on the Hamiltonian. So you can develop a Hamiltonian bound, and as you sample more, you get a better and better approximation of that Hamiltonian, which becomes a guaranteed under approximation of the ground truth Hamiltonian, but we're computing level sets of that, so that becomes an over approximation of the actual reachable set. Okay, sorry, an under approximation of the ground truth safe set. Here we're looking at we don't have a disturbance, we're looking at the control only. So we used actually an old model of a tilt ring. This has actually been flown. It's a NASA Boeing test vehicle that's been flown for decades. It's flown very conservatively during this transition mode. And based on this online computation of the Hamiltonian under approximation, is that working? Yeah, you can develop a kind of safe experimental method where you start out with a set that's known to be safe, and by judicious collection of data, you can grow that set and operate safely while you're growing it. And we've recently submitted this work. So this is a three-dimensional projection of that transition mode as you're going from vertical to horizontal. So, and this shows like that set from an initial safe tube, which you assume you have, over the number of iterations of solving this, first of all, sampling and then recomputation of this approximation of the Hamiltonian, you can get to, here it's about half of the volume of the ground truth safe set, which is shown here in gray, recovered after 19 iterations. So what does 19 iterations mean? That's, it depends on the overall, what does that mean in terms of the overall real time of the system? So this is going to be done right now, it's being done offline. But this is one of the most promising methods that for computing an approximation of that set for unknown dynamics that we've seen, and this is really hot off the presses. We just submitted this. Okay, I have about 5 minutes left, so I'm just going to, I have about 10 minutes left, so I'll just now move into going back to where we started. So I've been talking a lot about the safety filter, and okay, different systems are going to be designed different ways. some car companies are ostensibly using end-to-end based learning methods. I'm kind of really thinking about the use of these modular, or thinking about a modular design where you have a model of the system typically that you're trying to control. You may have some model of the interaction between agents in a multi-agent system. Control and planning, at least in the near future in safety critical systems, are likely going to be model-based methods, maybe augmented with learning-based methods. Perceiving the environment, predicting the behavior of other agents, that this is going to be learning based, and prediction, that itself is interesting. I think it's going to be either a combination or it's going to move towards learning-based methods. So the ability to quickly predict the behavior of other vehicles around you, other agents around you. It's pretty clear that the learning-based methods are beating out models that we've assumed about game theoretic interactions. But maybe there's some interplay between those model-based methods and learning-based methods that can be used. In any case, I think really going forward, it's going to be important to be able to capture, represent and capture the uncertainty, which I've represented as some variable or set of variables sigma, from those learning-based components, and propagate that uncertainty through the control loop so that the safety filter is safe, not just with respect to the kind of traditional things that we've been using, but also the insertion of these learning-based components. And this is the part of the Assured Autonomy project that I talked about earlier, where one of our capstone demonstrations with Boeing was a runway incursion problem. So now this is, it's actually a very safety critical situation. The aircraft is coming into land, something's on the runway, it wasn't observed quickly enough, or its behavior wasn't predicted, and there's an issue. And so being able to observe, even when you're several miles out, and what you see on the runway is basically like a pixel or two of another agent, being able to observe and then capture and then, bound and then predict what's going to happen and should that runway landing be aborted is something that we were working on. And that involves both perception and prediction. We worked quite closely on building a prediction module, a learning-based prediction module. And like I said, characterizing the uncertainty coming out of that prediction module and integrating it into the decision-making process of planning and control. And so part of our work used this, we developed this pipeline. A lot of these components are, our existing components. So this, the prediction module, we were using a retrained version of Marco Pavone at Stanford developed Trajectron++, or his group at Stanford and NVIDIA developed Trajectron++. That's a module that we used, and we had added some of the Boeing data to, in a sense, it wasn't fine-tuning, but it really was fine-tuning that model. Capturing not only the prediction of the other agents, but also there's different measures of uncertainty that you could use, whether it be the spread around the most likely mode or the distance between competing modes for that trajectory prediction. And then using statistical methods of quantile regression and conformal prediction to be able to take that uncertainty and turn it into an uncertainty which is which represents the uncertainty of the control action of the agent that you're looking at, that can then be used in a reachability-based framework to turn that uncertainty into a state-based uncertainty. So what it becomes is an expansion, like a buffer around the reachable set, which is specific to the uncertainty of that system. And that buffer, changes as the training data. So it's based on how you train the system. The more data you get, you can look at the sensitivity of that statistical buffer. And then we use that in planning. So you're trying to do the planning of your own agent with respect to these conformal prediction-based reachable set calculations of the other agents. And we did some we did some flight. Actually, we were up with Sanjit, who's also on the Assured Autonomy project. It was really cool to be able to work with Boeing and go up and do flight tests in their testing site in northern Montana, and test out these algorithms. And we continue to work with them on a number of problems. But how these uncertainty measures are now used in design, this is the work of Sampara Deglekar in my group. But thinking about now, suppose you have a design pipeline with different methods for planning and prediction. How do you use this uncertainty to evaluate different planning methods? And how do you use this uncertainty to evaluate different prediction methods? And so she's been looking specifically at using, so it's like a meta reachable set calculation, computing level sets for this uncertainty problem and using it in design selection. I'd like to conclude with some of our current work that we're doing. So this is just kind of going back to what I said at the beginning of the talk, that it's not going to be enough just to kind of do the safety-based calculations that we've been doing for, even if we're bringing in AI and thinking about uncertainty and growth of these, but like the reachable set are really in the dynamic space of the vehicle, so they're low dimensional, but how to really characterize that uncertainty and be able to develop formal proofs of the effect of putting a learning-based module into prediction, into perception, is something that I think we're all struggling with. And it's clear that we're going to have to better understand the behavior of these learning-based modules. And so one of our current projects, again with Sanjit, is on this idea of neurosymbolic programming, being able to really think about the structure of the neural net and how that contributes to the uncertainty in the output of the neural net. And so some of our recent work, which we've just submitted, is on going in and looking at developing a mechanistic interpretation of the tokens of these. In this case, we're using a vision language action model to control both in simulation and in our lab experiments with some manipulation-based problems. So all I want to say here is, I feel it's going to be very important to develop an understanding of how these VLM, VLA models are representing the system, and then be able to use that representation into the characterization of uncertainty. So I'm going to conclude by saying that a lot of what has been done so far in terms of control systems and safety critical control has been in automating platforms. And we've needed to make guarantees about how these platforms behave, even as they learn and evolve, and that includes how they interact with others. I think the future is really going to be about automating systems. So thinking about the overall behavior, like multi-agent systems we talked about, the integration of human behavior into automation is a big deal. So as we think about this evolving field of foundational models in robotics, I really think that we should be thinking about systems that are going to use these tools and methodologies, and I think systems of systems, people and robots, multi-agent systems, problems that aren't very well characterized and that don't necessarily work well with today's model-based control theoretic solutions. So with that, I'd like to conclude and thank a whole bunch of students, former students, collaborators in different groups that we've been working with, and open to taking any additional questions.
Thanks for a great talk. Are there any questions? Well, while you think about your question, I do have one. You said we need these guarantees, and I can imagine that there's also a certification aspect to it if you want to fly humans in an autonomous taxi. So do you have any ideas on how is that going to look like? What is the kind of material that we need to submit to certification bodies to get the authorization to fly humans?
I think there's a lot of work to be done there, but I can tell you that I've been involved in a number of studies and working groups in this, and the pathway is going to be and has been the looking at today's system, say what is done today, when the control is not automated, or I mean, it is automated, but the authority rests with the pilot or the air traffic controller. So there's really, in a safety critical system, it's human centric. That decision making right now is still human based. So they're treating, for better or for worse, the automation like a human. They're saying, okay, we have all these, see, detect, avoid. We have these procedures for what humans do. Can we then, if we treat that automation like a human, can we certify that automation? Can we just use the same procedures? That's not necessarily the right way to go, but it's the way that, automation in air transportation has been introduced. Like if there's see, detect, avoid is something that we worked on. There was a National Academy study actually about 10 years ago on this, and they were looking at, okay, we're going to, if you're introducing automation to do see, detect, it has to comply with everything that is required now if it's a human-based system. Okay, so, that's interesting. How do we do that going forward is, it's being developed, and I think it's a very good question.
Thanks. Any other questions?
Thank you.
Then let's stop here and take the rest of the line.